All right, so we're getting ready to do the calculations here. So there's the Cornell plate over on, let's see if I can, the Cornell plate there, and it was projected onto the board over there. I measured that distance from the Cornell plate to the board, and that was 1.39 meters long. This is the classic Cornell plate here. I was using the second one right here. There were 2 slits. And so, actually, the numbers are telling you the number of slits there are. So there were 2 slits, and that is the width of each slit, and that's the distance between them. So that 0.35 millimeters, so if you look over there, millimeters, so that's 0.35 millimeters between the slits. So D is 0.35 millimeters, or 0.00035 meters. We do need it in proper units in order to get a meaningful answer in the end. These are the marks that I made when we were doing the experiment. And so the one I drew the arrow to, this is the brightest spot right here. So this would be n is equal to 0 using the notation from the previous video. So n is equal to 1, n is 2, n is 3, n is 4, and then negative going to this side. So let's move that out of the way. So -1, -2, -3, -4, -5. So why is this side positive and that side negative? Because I just started out, it doesn't really matter which side you make positive, which side you make negative. Now, because we're dealing with such small distances here, the distance between any 2 of these should be roughly the same. If we were dealing with points out here at that point, then using one of our small angle approximations not going to hold anymore. But what I'm getting to is that this was the generalized formula right here, but I'm making the claim that we can get away with this version right here. So this was the second one I had done on the board in the other video. So if we solve for the wavelength, we get the wavelength is equal to D times Y, which is the distance from here to whichever spot I'm talking about, divided by L, that's the distance from the board to the Cornell plate, and divided by which value of N we used over here. So because all the distances are roughly the same, if I want to know the distance from 0 to 1, in other words, let n equal to 1, then what I end up with is basically the same distance here, 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 and here, or close enough. So what I did is I measured the distance from here to here using the vernier calipers. Show that that lines up if I get the coordination here. And then looking at the measurement here, I saw that the distance between the outermost ones was 24.50 millimeters. There are 9 sets of spacing there. There are 10 lines, so 9 spacing, so divide by 9. And what you end up with here is that is the distance between the marks, between the bright spots, or converting into meters, 0.00272 meters. Plugging it into our equation, I know that the wavelength is equal to, see if I can get that to focus, dy over ln. I'm going to let n equal to 1, so our d, that's the distance between the slits, 0.00035 meters, times y, which is the distance between here, so that is the 0.00272 repeating meters, divided by L, the length distance to the board, 1.39 meters, times N, which I chose to be 1. In other words, this distance right here is the distance between 2 sequential. If this had been 2 here, I would want a distance between, with 3 lines, the distance between the outer 2 lines. So, plug it into our handy-dandy calculator. And there's the calculations I'd already done, but let's just do it from scratch here. 0.00035 times 0.00272 repeating, divided by 1.39, and we end up with 6.85 0.8545 times 10 to the negative 7th meters. So is that correct? So let's put this in a slightly different form. I know that a nanometer is 10 to the negative 9th meters. So I want to convert this into nanometers because that's generally how wavelength of light is expressed. And so I'm going to multiply, actually we're going to flip it over, so 68545. So 6.8545 times 10 to the negative 7th meters times, I'm getting rid of meters, so 10 to the negative 9th meters is 1 nanometer, and I end up with 685.5 nanometers. One too many loops there. Nanometers. All right, so is that accurate? Well, in terms of what the box tells us, so this is the laser came from this box right here, and if we get in close, and hopefully it will focus, still hoping, pull back some, there we go. The wavelength that is expected is from 635 to 670 nanometers, should be a lowercase m, 635 to 670 nanometers, and we were at 685. We are just outside the range, but not bad considering the crudity of the experiment. So we can get, hopefully, better results when we do the diffraction grading. So I'm going to stop this one here.